We start this afternoon by the talk of Professor Michael Jolly from Indiana University, determining forms for the Navier-Stokes equation and nonlinear Schrödinger.
Thank you. It's great to be back in Rio. Nice to see a lot of good friends. Ricardo, too. So I'm going to talk about several types of determining forms. The talk will be basically in three parts. First will be one based on Fourier modes alone for the Navier-Stokes. The second is a more general approach using feedback control. And those two works are with Cyprian Foiash, Rostislav Kravchenko, and Idris. And then the third part, which for those who were at Guanajuato last summer is the new part. That's with a student at Indiana, Taral Sadegov, and Idris. And that's using the feedback control approach for the nonlinear Schrödinger equation, damp-driven nonlinear Schrödinger equation. Okay. So the basic idea goes back to determining modes about 50 years ago, which says basically that if you have two solutions on the global attractor, and I write this for a general system which fits the Navier-Stokes framework, two solutions in the global attractor, if a projection agrees on the entire trajectory for those two solutions, then they must be the same solution. That's what we mean by a determining projector. Now what we want to do, the basic idea, is that we want to extend the map that this defines from the spaghetti of projected trajectories down in the finite dimensional space, P of H. We want to extend it to that entire space, from the set of projected trajectories to an entire space. In that case, it's going to be the space of continuous bounded functions from the reals into the finite dimensional space. So we're not going to find a finite dimensional ODE. We're going to find an infinite dimensional ODE, which in some sense is going to be even bigger than the original infinite dimensional ODE. However, the original infinite dimensional system is not a true ODE. Only formally it's an ODE. This will be a true ODE in the end. That is, it's got a globally Lipschitz right-hand side, so it's a true ODE. So that's just a picture of what we mean by determining modes. You cannot have two solutions in the global attractor which have the same shadow when projected. So the first example is going to be Navier-Stokes, just to set the notation. This is the usual notation. B is the bilinear term. A is the Stokes operator. Lambdas for the eigenvalues. P for the projector onto Fourier modes. And G is the Grashof number, which is sort of our measurement of how efficient this is going to be in the end. I'll use a single bar for the L2 and a double bar for the A1 half norm, as is traditional. Now, it's been known for some time that the Navier-Stokes has a finite number of determining modes, and in fact, it's on the order of Grashof number. This parameter on the previous slide. And it's rather easy to show that if you use the definition that I just gave you. You just look at the difference of two solutions which have the same projection. They're on the global attractor. You take the scalar product with U. You rewrite the nonlinear term in this way with U1 in the middle, one of the two solutions. U is the difference. Okay? Do L4, L4, L2, and Leda-Zhenskaya, and ultimately you set up a Gronwall estimate where if you take t to minus infinity, which you can do because you're on the global attractor, then you find that, in fact, U, which is the difference, is 0, provided that m is greater than some constant times g, the Leda-Zhenskaya constant, in fact. All right. So we've defined a map on the projection of all the trajectories in the global attractor, and now we want to extend this. You can think of it this way. We define capital W from that set there in the squiggly brackets, and it consists of all bounded solutions to this equation, all bounded solutions W. So now we want to extend it to the space we'll call X, the space of bounded functions, into the finite dimensional space. As is common, we'll have to use a cutoff function, just for technical reasons. And here's the first main step. So now we take an arbitrary function in what is ultimately going to be our phase space, the space capital X. And we drive, in a sense, the W equation with that. So we're not taking a solution on the global attractor anymore. We're taking a function V, and we're sticking that inside B. V is a low-mode component, but it's the entire trajectory. You'll notice we're using S here for the time variable, and it's going to be a little confusing. Later I'm going to use T because there are really two time variables in play here. If you look at the space X, every element in X is a function of a real variable. That's going to be S ultimately. But later we're going to derive an ODE that's going to evolve, and it will have a time variable denoted by T. Just to warn you. In any event, if we take enough modes, and again on the order of G, we know we have a unique bounded solution, call it W, little w, and that will define a mapping, we'll call that capital W, which in fact is Lipschitz, and we can estimate its Lipschitz constant. So this factor beta is rather harmless if you look at it a while. You can see, well, it's got a logarithm term in M, so that's not big. And as far as the Grashof number goes, well, you've got Grashof upstairs and Grashof downstairs. So it's really not going to inflate things much. The point is that you can still take M on the order of Grashof, really. Okay, so I'm going to call this the determining form of the first kind. Sounds a lot better than the first determining form. Makes it a little fancier sounding, okay. In this case, we insert the map W where the high modes are supposed to be in the original equation. Now we've got a cutoff phi in front of V, and of course we're going to ultimately take that cutoff outside a large enough ball so we don't interfere with trajectories on the global attractor, the Navier-Stokes. But the point is that this is, in fact, a true ODE. F is globally Lipschitz if you write it as dV dt equals f of v, take everything to the right-hand side. And there's its Lipschitz constant in terms of that other Lipschitz constant W. You're saved by the fact that the former differential operator A, the Stokes operator, is now restricted to a finite dimensional space. Of course, all the work is buried in W. So the real motivation for this comes from inertial manifolds. So let's recall what inertial manifolds are. The idea was that you would find a finite dimensional ODE that has the same dynamics as the Navier-Stokes. And if you had such a manifold here written as the graph of a function on the left, you could substitute that for the high modes, phi of p in the upper equation. Traditionally, we would put a cutoff function outside of b in that case, but that's beside the point. So what you have here is a ODE in Rm, where m is the number of modes. The catch, of course, is that now after 30-some years, we still don't know whether there is such a manifold for the 2D Navier-Stokes. So we're going to get a poor man's inertial manifold, or a poor man's inertial form. We're not going to get a finite dimensional ODE. We'll get this infinite dimensional ODE, but an ODE. The determining form, where we substitute W for the high modes. The phase space is this space of bounded functions, X. Pictorially, the function phi has no time element, whereas the function W, to construct it, we have to consider entire trajectories. And in fact, when you get down to the point where you're actually trying to compute these things, say you want to evolve the determining form, you want to calculate W, it's, although a lot of work, computationally, or the complexity is big, it converges when the algorithms for computing inertial manifolds do not. And that is because you're feeding it more information. You're not just giving it the initial point in the finite dimensional space and then finding the one bounded solution backward in time that corresponds to it. You're giving it the low mode trajectory in its entirety, or in fact, it's enough to give it just in the past, and that will determine the one solution that's on the global attractor. Now, for this to be meaningful, we can write down an ODE that's derived from the Navier-Stokes, but it should have some connection with the Navier-Stokes, the long-time dynamics of the Navier-Stokes. First of all, it should have the property of being dissipative, just like the Navier-Stokes, and it does. Here is the radius of the absorbing ball. But also, in particular, trajectories on the global attractor have a natural characterization, a natural association with trajectories, certain trajectories for the determining form. Every solution on the global attractor for the regional Navier-Stokes corresponds to a traveling wave for the determining form. Every traveling wave corresponds to a trajectory for the Navier-Stokes. This is because we have these two variables, these two time variables. There's the evolutionary variable for the determining form, which I'm writing as t, but every element v is a function of time as well, whose variable we denote by s. So this theorem just says that we have that connection. Now, this is not meant to be the most practical theory in the world at this point. However, I can demonstrate it on a simpler problem, Kuramoto-Sierpyczynski equation, which has the same form and some interesting dynamics in its own right. So here it is with periodic boundary conditions. So in the way I've written the equation before, it's easy to spot what you would call A. We'll take it to be the bi-Laplacian, and B are the other terms, which includes a linear term, but it's got a parameter alpha in front of it. And of course, we're going to demonstrate things using the Galerkin approximation. So I'll denote that with U super M. So this first picture is just to demonstrate the traveling wave phenomena. So here you see two axes labeled S and T. So when T is 0, that periodic trajectory you're seeing, that's just for one component of the Galerkin approximation, V1, the first component. So there's the S variable going this way. And as you advance T, as you evolve the determining form, indeed, it just travels. That's because we're starting with a solution that's on the global attractor of the Kuramoto-Sierpyczynski equation. In general, you take a periodic solution, and it will remain a periodic solution, whether it's on the global attractor or not. In particular, if you have a constant solution that's independent of S, it will remain a constant solution. Now, it's possible that you could have a periodic solution. You feed that in as an initial condition for the determining form, that it will evolve toward a constant solution, but it'll do so through periodic functions. And I'll demonstrate that here. Here's the initial data, again, and along the x-axis. Here I'm taking the second component. And as t evolves, it remains periodic with the same period, but in fact it approaches a steady state. Now, to move on to the determining form of the second kind, there are two issues. One is, okay, what's the analog of the map W? And that's going to be found using the idea of data assimilation, which also goes back almost 50 years. We heard a little bit about this in Deborah's talk, and we will again tomorrow in Asil's talk. So the idea here, again, you have the equation of the same form. You're going to feed in a low mode trajectory, we call P1, and you can take as an initial condition an arbitrary high mode component. And this will drive you toward the solution U1. In other words, if we take U1 and we project it, it doesn't have to be on the global attractor. Just take a solution in Navier-Stokes, project it, take the P1 component. You can recover the high components by solving this equation forward in time. And Eric Olson and Idris in 2003, they found conditions on F which give you this convergence as you go forward in time. Now, the other piece for this second type of determining form, the feature is that it's more general. We're not just talking about determining modes anymore, but potentially determining nodes, finite volumes, finite elements. Or in general, we'll have a linear interpolant operator J sub H. So H is meant to be maybe the nodal spacing. And if you satisfy a condition that the interpolation there, Ju minus U, is something like H squared times the Stokes operator applied to U in L2, then you take two solutions in the Navier-Stokes. If H is small enough relative to the Grashof, and you have these two solutions approach each other forward in time, when you project with each element Li in the projector J, then the two solutions in their entirety must approach each other as t goes to infinity. But to try to use the general interpolants, say nodal values, with the same construction that we did for determining forms of the first kind, there's an issue there because you don't want to try to substitute into the nonlinear term nodal values because you have to take a derivative. So this is why we're going to use this idea of data assimilation, in particular feedback control. To do this, we're going to have some stronger assumptions on the interpolant operator J. So we assume both these conditions, so we've got a bound both in the L2 norm and in the gradient norm. Also assume that J applied to W has mean 0. So we can do this in nodal values. We can do it for Fourier modes as well, just to be consistent. So here's where the feedback control comes in. So let's take a solution in the global attractor. If it's a bounded solution to this equation, the W equation, where here we're forcing on the right-hand side with the solution that's in the global attractor, the only bounded solution is U itself, in which case that term would drop out. Provided that you take mu large enough, and once you've chosen mu, here on the order of Grashof log Grashof, then you have to take H small enough. So this is the analog of taking that spaghetti of trajectories for the first kind of determining form. That's automatically defining a map upward into the full space. Here, we're restricting ourselves to solution on the global attractor, and now we need to extend this to an arbitrary function v instead of u. So the function v is going to be in the ball. Here we won't specify the radius, a ball of radius rho in this space x. X is now not just bounded functions, but it's going to be C1 bounded functions with this norm. So there's a parameter k, not a parameter, there's a constant k that's here depending on Grashof, on the order of Grashof. And if mu is on the order of k squared log k, and then having chosen mu, if h is small enough relative to mu, then again, this w equation, where u is replaced by the arbitrary function v, this has a unique solution. And now this defines our map, capital W, from the ball of radius rho into y. So, just like you go outside here, you see two types of monkeys. Here we have the second type of monkey. It's a little squirrely, like the little guys out there. You see no resemblance to the original equation, to the Navier-Stokes form. The only way the original equation comes in is through this map capital W, which we've buried inside a soup norm. This x0 norm is the soup over the entire S trajectory. The soup of the difference between the function we're evolving v and the interpolant projected of the map W. And then in case, say, 0 is not on the global attractor, which is an issue in itself for the Navier-Stokes, we will take the difference, we'll take any steady state of the Navier-Stokes in the global attractor, and we'll just take the difference between v and that steady state projected. The whole point being that, again, we want to have a connection between the dynamics here and the original dynamics on the global attractor of the Navier-Stokes. The connection is not now with traveling waves for this new system, but rather it's with steady states of this new system. That is, every steady state for this determining form of the second kind corresponds to a trajectory on the global attractor of the Navier-Stokes. The projection, that is. That is, v as a steady state will be the projection of some solution on the global attractor. So this is an ODE in the true sense, in that this right-hand side is now Lipschitz on this ball. A ball taken sufficiently large so that all trajectories in the global attractor are going to lie in that ball. And that's related to the interpolant applied to u in this x norm. So what we've got is really a locally Lipschitz function. And we want this to be an ODE, so we need it to be globally Lipschitz. What we're going to do is take that ball big enough, and now we want to show that this ball is invariant. So if we just take v tilde to be the difference of v minus j u star, which appeared in the form on the right, so we're just substituting for the last term, and then we have to rewrite the norm term. So the v tilde equation rewritten on the top is like that. And then if you take the derivative with respect to s for that, there's only one place on the right that depends on s, that x naught norm, well, that's a sup norm. So s is gone. So you've got the time derivative dt of the s derivative, which we denote by a prime, is equal to that norm times, again, v prime. So then you can just take this scalar product with v tilde and respectively v tilde prime in each case, and you get these two decaying situations. You've got a negative prefactor in front of the variable double norm of v tilde, and likewise for v tilde prime. So those things are decaying, so you know that on the boundary of the ball you're pointing inward. So that's the invariance of the ball. And now we have to show what we promised, and that is that F is Lipschitz. Okay. So we can let F be denoted by some function g squared, that's the norm squared here, this x naught norm, times v tilde. The determining form takes that shape once we do the substitution. And then we look at the difference, f of v1 minus f of v2 in the x norm. Okay, split it up a bit. The second term, well, that's already set up for a Lipschitz estimate. So we deal with the first term. We just want to show that that satisfies a Lipschitz condition. And if we rewrite that here in terms of JW and then reorder things after doing the sort of backward triangle inequality with the minus signs, then you get two pieces, one that's naturally Lipschitz, and the other comes down to the Lipschitz constant of JW, that is the projector applied to W. So we let delta, little delta, be the difference of the W's. So we're talking about J delta. We have to estimate J delta. J delta you can split up again into two pieces. You've got delta itself. That's a good Lipschitz term already. And then you've got A delta. So now we have to estimate those. So to bound those, you have to make successive energy type estimates on these four equations. W, W prime, which is the S derivative of W. So you've got like the second derivative with respect to S there, but in terms of just W prime, the second equation looks like that. And likewise for delta and delta prime, the S derivative of delta. So you do all that, and ultimately you show that you can control delta. Okay, let me move on to the third part, nonlinear Schrodinger. So you might say, okay, now you're just going to go and do this for all the possible equations you can think of that have a global attractor and maybe don't have an inertial manifold, so there's some motivation for this compromise. And, okay, maybe we will. But the point is that in this case, it's a little more involved. It's not going to be just turn the crank like we did for Navier-Stokes. And the reason is that this is only weakly dissipative, or it's just damped, really. So it's going to require some different techniques in order to go through the analysis. Now, this damp-driven case has been studied before. Gedalia showed that there was a weak attractor. Wang in 95 showed that the weak attractor is a global attractor. Goubet showed that it's in HK if the force is. And Oliver and Titi showed that it's real analytic if the force is. So we have to define the phase space. Again, that's going to be bounded functions, bounded C1 functions. And the norms will look similar. And we have to consider taking an arbitrary V. So we're doing the data assimilation approach. We're going to restrict ourselves, however, to the Fourier mode projector. And the reason for this is that we don't have the dissipation that would normally absorb higher derivatives as we do energy estimates to get a priori bounds. So this is the W equation that will define what we call the W map. And we can show that this has a unique bounded solution, which defines our capital W. And for sufficiently large mu, and once you've chosen mu, sufficiently large M, then this will be a locally Lipschitz map. PMW, that is a locally Lipschitz map. So the analysis, I say, is a little involved. We do some estimates, and then we're going to refine them. So the first estimate is L2, right? And that's straightforward, but it's rather crude. We're going to drop that mu PMW squared L2 norm on the left in this first crude step, apply ground wall, and get this bound that's on the order of mu to the 1/2. There's some tension here with mu, and ultimately we need to get our bounds to be small in terms of mu. But using that first crude bound on the L2 norm, we'll get a first crude bound on the H1, and that's going to require this functional. Thank you, Charlie. So what you do is you get a ground wall estimate in terms of this functional, and this is what's interesting about the analysis of a nonlinear Schrodinger. You can't just work directly with the norms. You use these functionals that are motivated by the Hamiltonian structure of the equation. In the end, you get a H1 norm of order 5/2 in this initial H1 estimate. However, now if you go back to the L2 estimate and you attack this forgotten PMW term on the left, you want to take advantage of that somehow. Right. We have the freedom to choose a large number of modes, so you split that up into the identity in Q, the high mode component, and if you take M large enough, you can make that less than 1. And doing that, what you can do is you can eliminate the 1/2 power of mu, and you get something that's O of 1 for the L2 estimate. Then you go and you use that into the H1, and I should have said do this in the H1 estimate, not H2 estimate. You get a H1 estimate of order mu, an improvement over 5/2. Now you get the first H2 estimate. Take the scalar product here with this complicated expression involving WXX, time derivative S, and WXX in conjugate with a factor gamma. You get another functional. You get a ground wall estimate in terms of that functional. And you get an H2 bound of order mu to the 4th. Use that and the same trick with the Q in order to refine the H1 estimate. You get that down to mu to the 1/2. Then you use Agmon here to get an L infinity bound on W. That's going to be mu to the 1/4. And the time derivative from the equation will be mu squared. All right. So here's the connection. All right, so take a mu in the global attractor and let W be the bounded solution of the W equation, where V is actually the projection of a true solution to the global attractor. Then if mu is large enough, and you can satisfy this now because we know that this K infinity is going to be on the order of mu to the 1/4, so we take mu bigger than that mu to the 1/4 term, and then having done that, take M big enough so mu to the fourth over m is less than or equal to 1, then u must be W. So here's the determining form of the second kind for the damp-driven nonlinear Schrodinger equation. It looks the same. U star is again a steady state for the nonlinear Schrodinger equation, projected there. Take the difference. So this is now an ODE in the Banach space, and again, you've got a ball which is forward invariant. If you restrict yourself to that ball, F is globally Lipschitz. And the ball is big enough so that every solution on the global attractor for the nonlinear Schrodinger is contained in that ball. So we're not going to lose anything. Now, the proof of that proposition involves yet another functional for the difference, W minus U. So we use this functional capital phi to analyze this equation, as does the proof of the theorem. We've got to show that W minus W tilde is Lipschitz, so we end up using this functional phi sub eta, which is, again, rather involved. So there's the determining form for the nonlinear Schrodinger, and kind of as a byproduct of that analysis, we get a new bound on the number of determining modes for the nonlinear Schrodinger equation. So you just follow through this with the same a priori estimates, but use them to estimate the number of determining modes, and it turns out to be on the order of the L2 norm of F to the 10th power and gamma to the minus 12. Now, Goubet estimated a number of, he didn't estimate the number of determining modes. He did the analysis, but you have to read between the lines and calculate what his analysis would yield, and it seems to yield F to the 12 and gamma to the minus 12.5. Now, gamma is small, you're thinking, because you're decreasing the damping. That should make the global attractor more complicated. So you would want a bigger, smaller exponent on bigger in absolute value, bigger in the true sense, less negative power on gamma, and a smaller power on F. Okay, so in 5 minutes that remain, I will, yeah. Oh, easy only in the sense that we've already done the a priori estimates in establishing the determining form. One has to trace through all those and see how things depend on L and F and yeah. I would have to check to be certain. Yeah. Sorry. Okay. So 5 minutes on some numerics, right? So to evolve the first kind, since it has this connection to inertial manifolds, Ricardo's not here, but I'll still cite him. We can adapt an algorithm for computing inertial manifolds. And as I said, we have an advantage here in that we're feeding it in a trajectory that goes in the past. So we're giving it more information, and indeed it converges rather successfully. What we're doing basically is we're finding a fixed point of a discrete contraction mapping defined by the variation of constants formula. Here you see it with script capital T. We discretize it by using a piecewise linear approximation, and as we take that finer and finer and go back further in time, we converge toward a solution. So here we'll take a particular solution on the global attractor for the Kuramoto-Sivashinsky equation. And here we take iterations of our discrete contraction mapping, and you see these approaching the top, which is the true solution for an 8-mode Galerkin approximation. Using just 4 modes, we're recovering the other 4 modes. However, if you look at the far left end in time, S, you see that initially it's not so good. You can't tell it on this scale, but on the far left end, things are not converging as well. And that's an issue if you want to evolve the determining form, because you need this to be accurate over the whole length of the interval in S that you're trying to follow. Another cute example to play with is a Lorentz system, because a single mode is determining for that, the Y mode. Because you can write X and Z in terms of the Y mode. A steady state equation for the determining form of the first kind then is actually a differential algebraic system. Written here, but that algebraic relation can be solved explicitly for Y. So that DAE corresponds to this ODE in just the 2 variables. And then you'll see that there's the usual Lorentz system, and now you have this extra element of the global attractor of the determining form plotted there with it. So the original Lorentz system would be realized as traveling waves, and then this guy is a steady state for the DAE, for the determining form. Okay, so for the second kind, you have this equation. You need to solve at each step this W equation. But you don't have to keep track of the whole W trajectory. All you need is the soup norm of the difference between V and the projection of W. So you can calculate that as you go along. And you need to calibrate it first if you're doing this. Empirically, you would need to establish, okay, how many modes do I need? Yes, there are estimates. We're doing it on the Kuramoto-Sivashinsky, which doesn't really make sense for determining modes since you already have an inertial manifold. Why should you do this? Well, we're just doing it for demonstration purposes. But here are a number of cases. Most of them are using 3 modes. And I'm varying mu, the factor in the feedback control here on the right. So the bigger we take mu, the bigger you'll get attracted to the correct solution. On the other hand, if you take it too big, it's natural that maybe you're adding some stiffness to the problem. So there's some sweet spot there where mu is 100, or rather 1,000. Take it to be 10,000, then it deteriorates a little bit. If you take it to be 100, it's not as good. Anyway, doing this, you can kind of establish that there's some time here, in the best case, maybe about 0.05, after which you know things have settled down and you've got a good W solution. So you can throw that into the determining form, and this is a boring example because I'm giving it a steady state, or what should be a steady state. I take a periodic solution for the Kuramoto-Sivashinsky, I feed that in as a function of S, and it remains such a solution. All right, so what you see from this is that you cannot just take a complete trajectory over some time interval and expect to evolve that. You're always going to lose a little bit at the beginning. Or schematically, here this V starting at 0, 0, that could be your initial condition going out to V0 of S. And you get from that a W solution associated with it, but it's tainted at first. So at the next step, at time delta t in the evolution, you would consider that to be the start of the trajectory. And then one more thing. So what could you do with this? Well, for the Lorentz equations, I'll take a solution that's on the chaotic attractor and then perturb it with some random values along the trajectory. So that initial condition is back there on the left, this fuzzy thing. And if you evolve that, what it does is it kills that noise. So usually you say, first of all, I want to thank the organizers. I'll just say, lastly, I should thank Milton, Helena, and Jim. It's great to be back. And with that, I'll quit.